George throws the ball at target 15 times. Each time he throws the ball, the probability of the ball hitting the target is 0.48. And the random variable x represents the number of times George hits the target in 15 throws. So we have a fixed number of trials, we have a fixed probability of success, either success or failure, and we're going to assume the trials are independent. This is a binomial distribution. Parameters 15, 0.48. So to work out the probability, quickest way is to just put it in your calculator. Distribution, binomial PD, variable, we're looking for x equals 3, n is 15, p is 0.48, 0.01966. Switch around to three significant figures, 0.0197. Of course, you should know how to get that without just sticking it in your calculator, and it's as follows. So the probability of getting 3 successes in a row would be 0.48 to the 3, and followed by 12 failures would be 0.52 to the 12. That would be success, success, success. Actually, I'll write that down. Followed by 12 failures, lots of them. But then we can obviously get 3 successes in a different way. It could be the last 3 are successes. We can arrange them. And so it's all about how we arrange these 15 objects where 3 are the same and 12 of them are the same. This is where the factorial function comes in. And the quickest way to say it is that it's going to be 15C3, because we're arranging 15 objects, there's 15 factorial ways, but 3 of them are the same, so we have to cancel out all the different ways we can swap them around, and then the same for the 12. So that is what that is. And if you put this into your calculator, you get exactly the same answer. For x greater or equal to 5, see we're adding up quite a lot here, but best to do 1 minus the probability that x is less than or equal to 4. Note that less than or equal to 4, we want to include 5 in it, so we just take away 0, 1, 2, 3, and 4. And for this, although we could do it, the long way by calculating all the individual probabilities, there's a handy cumulative distribution function which does less than or equal to. So just put in 4, 0.07986, which then becomes to 3 significant units 0.920. Right, well done so far. George now throws the ball at the target 250 times. Use a normal approximation to calculate the probability that he will hit the target more than 110 times. So I first of all constructed another binomial distribution, A, because it's not the same thing, it's not X anymore, because X was when, it was 15 trials. So I used a different parameter. It's not, sorry, variable. It's not essential. I think it's good practice. So 250 and 0.48. Should we define it? Okay, I'm going a bit overboard, but A equals number of times George hits target from 250 throws. But we want to use a normal approximation. So let's say Y, or actually let me say that A is approximately Y, which is then a normal distribution, and we can work out the mean and the variance. There's a handy formula given in the formula book for this. First one's quite intuitive, like if you flipped a coin 100 times, you'd expect to get 50 heads. That would be your expected value or your mean, because it's just a number of trials times the probability. Same thing here, 250 times 0.48, that ends up being 120. The variance is a little bit hard to kind of visualize or anything, but you can prove it using like summations. This is not on the A-level course, but anyway, yeah, we just times by 1 minus p, so we just times by 0.52, and that gives us 62.5, sorry, 62.4. That's the variance. I'm going to write it as 62.4 rooted and then squared, because then I also get the standard deviation. Just make sure that that's the one you're putting in your calculator. Okay, so we want the probability, get rid of that now. So going to get rid of this, it's kind of getting in the way. Probability that A greater than 110, no, more than, so it can't equal it. That's going to be approximately equal to the probability that Y is greater. Okay, it's actually not 110 because what we need to do is a continuity correction. We are trying to model a discrete distribution with a normal curve. Okay, and that's not bad, is it? But you've got to kind of remember that you're actually sort of broadening this out and making areas. And it's not going to be perfectly overlap. So I want the probability that A is greater than 110. So this is like the very center. I broaden them out so I get an area, basically, for my binomial, rather than just a height. I want it to be greater than 110. So actually, I don't want to include this bar, which means with my continuity correction, I'm going to go greater than 110.5. I haven't gone into a lot of detail on continuity corrections here, but I'm hoping you're somewhat familiar and I'm just kind of jogging your memory on it. If it was greater or equal to 110, then it'd be 109.5 because we want to include this bar. Because it's greater, I just want to include this bar, everything then to the right. That's very important. You have to get that in to be as accurate as you can. And then it's just a case of using our calculator one more time. Distribution, normal CD. Lower limits are 110.5. Upper limit, just a significantly large number. Standard deviation, that's our roots, 62.5. Sorry, 62.4. And then mean 120. Which gives us 0.885 to three significant figures.